Now, let's say why AI lives in 10,000 dimensions. Why AI lives in 10,000 dimensions as we continue with the mathematics of artificial intelligence. So, the learning objectives here include this, that by the end of this lesson, you should understand what a dimension means in AI and machine learning, what feature representation means, why modern AI systems use thousands of dimensions, how embeddings work, why high dimensional spaces are useful, how large language models, that is LLMs, and recommendation systems use high dimensional representations, and the advantages and challenges of high dimensional learning. So the key idea here is this, that modern AI systems convert objects into vectors. We've said that for the umpteenth time. So since we started, then these objects can be words, sentences, images, users, products, movies. Each object becomes a point in a high dimensional space, and a vector might contain 768 dimensions, 1536 dimensions, 4096 dimensions, 10,000 plus dimensions. So the position of the point captures information about the object. So the central idea is that AI transforms meaning into geometry. We've been talking about that a lot. So I think in the second, in one of the earlier videos, I talked about how AI converts words into vectors. So it's still the same overarching idea. So question is, what's the dimension? A dimension, of course, is a measurable feature used to describe an object. For instance, if you talk about two dimensions, suppose we describe a person. So you can describe a person using many realities, many variables. But some of the key ones are height and weight. In fact, with height and weight, you can measure things like BMI and the rest of them. So if you describe a person by height and weight, then a person becomes height and weight. For example, height 170, weight 65 kg. This is a point in a two-dimensional space. And that's how dimensions come about very easily. Then imagine we talk about a human being in 5 dimensions. So now you want to add age, income, and years of education. So the representation then becomes height, weight, age, income, and education. So height 170, weight 65, age is 30, income 60,000, education 16, right? So years of education is now 16 years. So this person now lives in a five-dimensional space. So you see how it's going? So every new feature creates a new dimension. So any new feature you add adds a new dimension to it. Now for feature representation then, machine learning algorithms operate on numbers. So therefore, real-world objects must be converted into numerical representations. So one underlying fact of AI we've always said is that human language is not known to machines, to computers. So you have to convert human language into numbers that computers understand, into vectors for that matter. Therefore, real-world objects must be converted into numerical representations. This process is called feature representation. So imagine if you have house as an object, the representation it's a feature object. A sentence, you have an embedding vector. A user is a preference vector. A movie is a latent feature vector. An image is a pixel or embedding vector. So these are possible representations of various objects. Now, imagine a house example. So a house has features like size, bedrooms, bathrooms. And in that case, a house can be represented as 2000 in size, maybe 2000 square meters or something like that, 3 bedrooms and 2 bathrooms. So this vector has 3 dimensions. So each coordinate represents a feature of the house, right? So 2000 represents the size of the house, 3 represent the number of bedrooms in the house, two represent the number of bathrooms in that house. So and each of them like that gives and they contribute something to the information about the house. So why few dimensions are not enough? Many real-world objects are extremely complex. Consider a movie with possible features including action, romance, comedy, violence, visual effects, sound quality, pacing, story complexity. A movie may require hundreds of useful features. So then you have uh, language, which is even more complex. So a sentence can contain information about grammar, meaning, context, intent, topic, emotion, and style. So a small number of dimensions cannot adequately represent all of these factors. Therefore, modern AI uses high dimensional representations. So talking about high dimensional spaces now, a vector with 10,000 coordinates represents a point in a 10,000 dimensional space. So imagine all those features we are saying about a house. Imagine trying having to get like 10,000 information about a particular house. By the time you are done, you would have finished describing the house thoroughly. So a general vector can be written as x which is x1, x2, x3 up to xn, where n may be thousands of dimensions. So humans cannot visualize such spaces because they are so too much information. So, however, mathematics still works perfectly on that dimension. So we can still measure distances, compute similarities, cluster points, find nearest neighbors, learn patterns, and the geometry remains valid even though visualization becomes impossible. So let's talk about distance in high dimensions. In two dimensions, Euclidean distance is d equals square root of x1 minus y1 squared plus x2 minus y2 squared. That's a very basic formula in coordinate geometry. Then in n dimensions now, you can then have summations. So square root of the summation from I equals 1 to n of x, all the x's minus y has raised to power 2. So the formula is identical. It's basically the same, except that this one can go for, it can have 1,000 dimensions here. So the only difference is the number of coordinates, like we said. So this allows us to compare complex objects represented by thousands of features. Then talking about similarity as geometry then, suppose we represent three objects, cat 0.7, 0.2, 0.9, dog 0.8, 0.3, 0.85, and car 0.1, 0.9, 0.2. Notice cat and dog look similar. The corresponding coordinates are similar. Then cat and car are totally different, 0.7, 0.1, 0.2, 0.9, 0.9, 0.2. So in vector space then, similar objects appear close together. The similar objects appear far apart, meaning emerges from geometric relationships. That closeness tells us something. And then we go on to talk about the idea of cosine similarity, which has been a regular feature in most of the videos I've been, putting up. So modern AI often measures similarity using cosine similarity, and the formula is simple. It's for vector dot product formula. So cosine similarity, cos theta, that the cosine of the angle between the vectors is simply x dot y, that's the dot product of vectors x and y, divided by the product of their moduli, where x dot y is the dot product and the modulus of x is the vector magnitude. By interpretation, then, we have that one cosine similarity of one means the vectors are in the same direction. Cosine similarity of zero means the vectors are unrelated, that is, they are perpendicular. So here they are parallel, moving in the same direction. Minus one means they are parallel, moving in opposite directions. Okay, so cosine similarity focuses on orientation rather than magnitude, and this makes it particularly useful for embeddings. Okay, so two things can be far apart by Euclidean distance, but they are really close because they move in the same direction. So given x to be 0.7, 0.2, 0.9, 0.8, 0.3, 0.85, that's like the cat and dog thing. So if you compute x dot y, that's 0.7 times 0.8 plus 0.2 times 0.3 plus 0.9 times 0.85. So you have 0.56, 0.06, and 0.765. If you add it all up, you have 1.385. So then the vector magnitudes now. So you have modulus of x, which is square root of 0.7 squared plus 0.2 squared plus 0.9 squared. That's square root of 1.34, and that's 1.158. Similarly, you have the modulus of y to be 1.206. So the cosine similarity will be x dot y all over the products of this and this. So 1.385 over 1.158 multiplied by 1.206. And that ends up giving us 0.92. So the vectors are highly similar because you get something pretty close to one. That's 0.992. That's very close to one, meaning that the vectors are highly similar. Then we talk about distributed representations. Early systems often used one feature per concept. Like example, is cat, is dog, is car, is tree. This representation is inefficient. Okay. So, but then modern AI uses distributed representations. I think the last question answered in the other video talks about how information is distributed across neural network instead of being stored in a particular place. So modern AI uses distributed representations. Instead of one dimension representing one concept, every concept is spread across many dimensions. So every dimension contributes to many concepts. So this is called a distributed representation. So the importance consequence is that no single dimension usually means cat or dog. Meaning emerges from the entire vector. So you can draw meanings from everywhere. So imagine embeddings like this. An embedding is a dense vector representation learned automatically from data. So an embedding is a dense vector representation learned automatically from data. In the last video, we had defined embedding as numerical representation of raw data in latent space. So another way to define it is to say an embedding is a dense vector representation learned automatically from data. So imagine king with the dimensions 0.2 minus 1.4, 0.8, and so on. Queen 0.3 minus 1.2, 0.9, and so on. Man 0.5 minus 0.8, 0.1, and so on. Woman 0.6 minus 0.6, 0.2, and so on. So embeddings place similar concepts near one another and they create a geometric map of meaning. So the question then is, why do high dimensions actually help? So high dimensional spaces provide more room for information. Suppose we classify cats, dogs, and cars in 2 dimensions. These classes may overlap. So, but if you add dimensions such as fur texture, so if you just talk about their friendliness and whatever, so we may have overlapping things about cats and dogs being friendly. But if you add things like fur texture, wheel likelihood, backing tendency, engine characteristics, this can make classes easier to separate. So once you add things like backing tendency, cats don't bark, dogs do, cats don't. So that really stands out cats. Engine characteristics, cats and dogs don't have engine in that sense, but cats do. So this can actually help to separate the ideas. So we see then that high dimensions create additional degrees of freedom. So this often allows machine learning models to discover patterns that would be impossible in lower dimensional spaces. Like we saw in the last video, we consider the curse of dimensionality. So high dimensions provide expressive power. However, they also introduce challenges. So the phenomenon is called the curse of dimensionality. Because of very big dimensions, it can be problematic, especially for humans. But then problem one is sparsity. As dimensions increase, sparse expands rapidly. I mean, space expands rapidly because we have a lot of space. Then data occupies a smaller fraction of the space. Because if you talk about ability to bark now, only dogs bark. So where you have cats and cars, maybe if you're assigning a score of 0 to 1, so you just have zero in those places. So, there'll be so many zeros like that. Now, you also see that even millions of observations may become very sparse. Then problem two is distance concentration. In very high dimensions, nearest points become less distinct and distances begin to look similar. So this can make similarity calculations more difficult. So these are two issues about the cost of dimensionality, sparsity and distance concentration. So as you have so much data, so the distances begin to look about the same. Then we have neural networks creating high dimensional features then to solve the problem of the cost of dimensionality. Neural networks transform information layer by layer. So you have a sentence, so it's layered into one. You have layer one, layer two, layer three, and then it is embedded. So we then see that early layers often capture characters and tokens. Middle layers will capture things like grammar and structure and syntax rather, and later layers will capture things like meaning, intent, and context. And then the final representation is a high dimensional embedding that summarizes the inputs. So let's look at application one of this in large language models, LLMs. Large language models represent words and sentences using embeddings. Typical embedding dimensions include 768, 1024, 1536, 4096, and more internally. A token is transformed into a vector. So you have token transferred into a vector by the process of embedding. So this embedding contains information about meaning, context, grammar, style, topic, and words with similar meanings occupy nearby regions in embedding space. For example, you have king, queen, prince, and princess, and they may form a cluster, while meanwhile, car, engine, and truck may form another cluster because they are similar. Then how LLM use embeddings now? Suppose the input is how do airplanes fly? Okay, the workflow can then be this. You input the text, how do airplanes fly? And then the text is broken down into tokens through a process called tokenization. Then the tokens are embedded into and then stored in embedding vectors. And then you have transformer layers working on them, which are like your models now. Then you have high dimensional hidden states, and then you can have next token prediction. And that's where you begin to get answers out in generative AI. So the model continuously transforms vectors in high dimensional space. Reasoning can be viewed as movement through this learned geometric space. Now, question again, why LLMs need thousands of dimensions? Language mod contains enormous amounts of information. So a representation must simultaneously capture syntax, semantics, word knowledge, context, sentiment, topic, intent, and style. So a small number of dimensions would not provide enough capacity. So that's why we need thousands of dimensions. And that is why we talk about AI living in 10,000 dimensions. So thousands of dimensions allow the model to encode many independent patterns simultaneously. This is one reason modern language models rely heavily on high dimensional embeddings. So for application two, now imagine we want to talk about about recommendation systems. Recommendation systems also use embeddings. Examples, maybe streaming platforms, online retailers, social media platforms. Of course, for instance, you watch YouTube and as you're watching, after you watch one, another video is recommended for you based on your pattern, how you've been using, the kind of things you've been watching, right? So streaming platforms, online retailers, social media platforms. So users are represented as vectors. So the vector users can be you, uh, so from U1 to UN, having n dimensions, then items are represented as vectors. So you have maybe the videos or whatever is being recommended. So you have starting from M1 to Mn. Both users and items live in the same embedding space like that. And then you now have recommendation similarity. Suppose a user, the vector for a user is 0.8, 0.2, 0.9, and action movie is 0.9, 0.1, 0.85. Then romantic movie is 0.1, 0.9, 0.2. So you see that these two, the user and their action movie are close together based on their interests, the kind of things they watch. But how do you do that mathematically? Recommendation systems often compute the score UM. That is, you have the dot product of the two. So then higher score implies stronger preference. So when you get higher score like that, you have a stronger preference. So for action movie now, if you work out the user and action movies, you get 0.8 times 0.9, 0.2 times 0.1, 0.9 times 0.85. If you put all of that together, you get 1.505. Then for romantic movie score, you have 0.44. That's like 0.8 times 0.1, 0.2 times 0.9 plus 0.9 times 0.2. So you have 0.44. So since 1.505 is greater than 0.44, then the action movie is recommended for that person. So all of that is done in the background without. So sometimes you're on Facebook or you're on YouTube, and then you finish watching a video. So a set of videos are recommended for you based on your behavior, because your behavior has also been embedded in the system. So that can cause matching. So it can easily match you with the kind of things you like to watch. So matrix factorizing and latent factors now. Consider user item rating matrix. So you have user one, two, three, and you have movies five, question mark four, movie B, question mark three, five, movie C, four, two, question mark. Now, instead of storing ratings directly, the system learns user as latent vector and movie as latent vector because the computer doesn't understand these things, but it just says the latent vectors. So typical latent dimensions can be like 50, 100, 500. These latent factors often capture hidden preferences automatically. So example, so as you're watching, each time you click, you are dropping information for the system. So example, sci-fi preference, maybe you always when you go on YouTube, there's a particular kind of thing you always go to search for. So maybe you have a preference for sci-fi or romance or humor without explicitly labeling those dimensions. So, I mean, probably computer the machine doesn't even understand it, but it just sees the kind of movies you like or the kind of things you like to watch. So a useful mental model will be this. Think of embeddings as GPS coordinates for meaning. So GPS uses things like latitude, longitude, and altitude to locate places. So AI then uses X1, X2, X3 up to X 10,000 to locate concepts. So the meaning of an object then is not stored in one coordinate. Instead, meaning is represented by its location in the entire high dimensional space. An object with similar meanings occupy nearby locations. So in summary then, we have the following that modern AI lives in high dimensional spaces. That's why we say it lives in 10,000 dimensions. So modern AI lives in high dimensional spaces because complex information requires many coordinates. And the key ideas are as follows. A dimension is a feature or coordinate. One dimension is a feature. Like when you talk about animals now, friendliness is a feature. Wildness is a feature. Furriness, whether they have furs or things like that. Then feature representation converts objects into vectors because machines do not understand objects. Rather, they understand vectors. Embeddings are dense length representations. So embeddings, put all the vectors together like that. Then similarity becomes a geometric concept where it computes cosine similarity, kind of. Then LLMs use high dimensional embeddings to represent language. Recommendation systems use embeddings to represent users and items. High dimensions provide expressive power, but introduce challenges such as sparsity and distance concentration. So the final takeaway is that modern AI works by transforming language, images, users, products, and knowledge into high-dimensional vector spaces where learning, similarity, prediction, and reasoning become geometric operations. So, I mean, we have some cosine similarity thing here. So if x is 0.7, 0.2, 0.9, and y is this now. So how close are they? If you compute the cosine similarity, you see you get 0.992, which shows that these two vectors are the same. So if these are any object these two are representing, means that so the answer means that the objects they are closely related. Now we talk about distance in high dimensions now. So if you have 2, 10, 100, 1000, and then you just pick them randomly to compare their distances. So you see in dimension 2, for instance, the minimum distance between 2 and the next is like 0.041. And the minimum distance in 2 dimensions, maximum is 1.162. But dimension 10, minimum is 0.681. And then the maximum is 1.744. In dimension 100, minimum distance is 3.423, and the maximum is 4.680. Then in dimension 1000, the minimum distance is 12.424, and the maximum is 13.605. So as dimensions increase, that distance begins to. So you see, the minimum and maximum, they are closing up rapidly like that. So that's the kind of thing about distance, distance. Was there's something, yeah, distance concentration, something like that. So as dimensions increase, the distances are close by, more closely connected. Then for recommendation system example now, imagine a user whose vector is this, and you have an action movie and romantic movie. So if you compute the cosine, yeah, if you compute the cosine similarity among them, or even the dot product, so you get 1.505. Okay, I think it was exactly what we did the other time. So, and then you have romantic movie score 0.44. So the recommendation would just be the active movie, the one that has the bigger score, like that. So we have practice problems. So as usual, we have 20 of them. So, and I get to solve two. So in this case, I'll be dealing with questions 11 and 16. Questions 11 and 16. So here I have 1 to 10. So I have 1 to 10. And then the other part now. Okay, we can see the rest together. Mathematical and analytical problem. So I'll be solving this 11, for instance. A user embedding is U, 2134, and an item embedding is M, 1221. Compute the recommendation score using the dots product. So yeah, and you have all the rest up to 14. Then from 15 to 20, we have this now. So I'm taking care of problems 11 and 16. So problem 16 talks about a large language model stores an embedding matrix of 50,000 tokens. Each token has a 1024 dimensional embedding. How many numerical values are stored in the embedding matrix? So let's go straight and deal with that as we begin to bring this to a close. So we start with problem 11. So for problem 11 now, so it says given given U, which is 2, 1, 3, 4, and M, which is 1, 2, 2, 1. The recommendation score, the recommendation score is computed using the product, using the dot product now, using the dot product score equals U dot M. So U dot M simply means we have 2, 1, 2, 1, 3, 4 dot 1, 2, 2, 1. So that means we have 2 times 1 plus 1 times 2, that's this times this, plus 3 times 2, that's this and this, plus 4 and 1. 4 times 1. That's 2 plus 2 plus 6 plus 4. That is simply 14. So the interpretation of this, interpretation, a, a recommendation, a recommendation system would compare this score to other items, to other items, right? Then larger scores indicate stronger similarity between the user and the item. That goes. And then we have so number 16 now. Yeah, problem 16. We say that language model, a language model stores first 50,000 tokens. So a token is, there's small chunks of words that are, used for embedding. So 50,000 tokens, then you have 1,024 dimensional, 1,024 dimensional embedding for each token. I mean, that's a lot, right? For each token. Each token has a 1,024 dimensional embedding, right? So then we see that the total number of values stored will simply be 50,000 times 1,024. Okay. Well, I mean, we can just compute this directly, but you can do some gymnastics, right? So this 50,000 multiplied by 1,000 plus 24. So that's 50,000 times 1,000, that's 50 million. 50 million times 24, that's 1,200,000. Put that together, you have 51,200, 51,200,000. And that's the answer. That's the number of values stored, in that model. So we can say that the so the embedding, the embedding matrix therefore contains 51.2 million views. Okay. So this illustrates why why modern AI models require substantial memory even before any neural network computations occur. occur storing storing embeddings storing embeddings alone may require tens or hundreds of millions of numerical parameters. Of course, and that is why these days we need a lot of data centers to hold most of this, to store most of this information like that. So with that, we come to the end of this interesting video on why AI lives in 10,000 dimensions. So look at the problems again. So here you have 1 to 10, then you have 11 to 14. I did 11 already. Then you have 15 to the end. Let me know how helpful this is for you. And if there's something else let me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. But if you have not subscribed, why not go ahead and do that right away? And hit the notification bell also so you can always get alerted each time a new video is released. If you also want to take it further and become a member of this channel, you can click on join. That gives you some special privileges, which you're going to find out as you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.